we are going to move on to our first contributed speaker of this session. And please correct me if I mispronounce your name, but I did look it up, so hopefully I'm correct. We have our next speaker from the ELTE University in Hungary, and her name is Katalin Solymosi, and I will let her get started.
Thank you very much, and thanks everyone for the possibility and for this fantastic organization. Can you see my screen and hear me?
Yes, we can.
Okay, thanks. So I will talk about some very specific area, but I think the method might be useful for those studying chloroplast structure and especially grana. So this is why I came here and try to present some of the data. So the chloroplast is where photosynthesis occurs. So it's a big jump from the fantastic mammoth story before this presentation. Grana are highly regular structure in which thylakoid membranes are piled on the top of each other and are interconnected by stroma thylakoids. Of course, chloroplast is where everything happens in terms of photosynthesis, so it's extremely important to see how its membranes and photosynthetic apparatus react to stresses. So when we look at literature data, either there is no change in chloroplast structure, or at least authors don't mention anything, or in some papers, similarly to papers related to how heavy metals or many other stressors, excess of metals or deficiency affect the plastids. Also, drought stress is often reported to cause a kind of swelling of the thylakoid lumen, so of the intrathylakoidal space, either on the top of the grana, or very often it's rather in this stroma thylakoid region. Then there is a kind of swelling reported, which is a little bit striking or strange, because one would expect that in dehydrated or low water level, or when there is a low water content in a tissue, swelling of an inner membrane, aqueous phase, the lumen, is not necessarily something one would expect. Of course, there are other changes in the plastoglobuli, but I will focus on the thylakoid membranes because this is what we have studied. We used a plant which is not very widely used as a model plant, but it's an ornamental plant that is quite famous for surviving very long periods of drought stress. It can even survive up to 60 days, but what we choose is that we did not water it for 45, 49 days. And what happens at this time period is that the leaves are rolled, and that is preventing or helping to minimize, of course, water loss by transpiration. And after rewatering, we were also checking the recovery on a shorter and longer scale. So I will show some results within few hours of rewatering, but on the long term. And then also for control leaves, we have compared younger ones and those which were close to the same age as the rewatered plants that we have checked. Data are published in this paper in Physiologia Plantarum. So especially using the methods and how we characterize the photosynthesis, I will just very quickly go on through because for the sake of the time. Of course, the soil is drying out very quickly, goes down up to 10% of soil water content. And then after rewatering, of course, it gets back to control levels. And surprisingly, the drying period resulted only in a decrease of the leaf relative water content up to 60%, which then gradually got to the control levels and the old control levels later on. Just to characterize briefly what is going on in the leaf, surprisingly, the chlorophyll pigments or the photosynthetic pigments do not change significantly. Also, the 77 Kelvin fluorescence spectra do not show any big changes in the control dry and then rehydrated plants. At the level of the chlorophyll protein complexes of the photosynthetic apparatus, surprisingly, they are remaining stable. I mean, that means that the plant is preserving them. Only slight changes can be observed, especially at the level of the photosystem 2, monomers are decreasing, and instead of them, we see a kind of accumulation or increase in the supercomplexes. And there are also some slight changes in the LHC2 and the PS1 complexes, decrease one. The photosynthetic activity, the maximum quantum yield of PS2 is basically not unchanged during dry and then the rewatering phase. And there is a slight decrease, which, well, a little bit is restored after rewatering, although it's not necessarily always full restoration. So this is what we observe at the physiological level. And at the structural level, of course, we observe this rolling of the leaf, which is a mechanism to minimize the water loss. And at the same time, leaf structure has, structural observations outline that there is a water storage hypodermal cell layer, which is really significantly decreasing under water stress. As you can see, embedding was a pain. I mean, sorry to say it like this, but it is really hard to embed a leaf which is quite dry, although not fully dry. But at this stage, we did not obtain very nice images of this cell layer. But then this is restored in the rehydrated and rewatered plants relatively quickly. We observe a slight change in the chloroplast length, but overall chloroplast structure, I won't go too much in details, but it was not much changed. We observed larger changes among different leaves of different control plants than between the stressed ones or the recovered ones. So it looks like plants are really efficient in retaining the chloroplast structure. And also the thylakoid system, we did not observe any swelling. And when we performed with ImageJ some fast Fourier transformation analysis of these grana that we could observe in the different treated leaves, we again observed a relatively large biological variability. So even among control plants, different regions of the leaves, there were quite big differences, sometimes even differences that looked significant. And that's quite a problem when we want to analyze and compare or study how the membrane, the repeat distance of these thylakoid membranes is affected. So the fast Fourier transformation data provide you the kind of grid value or a kind of distance between the repeat distance value in a granum. So it looks like fixation has several limitations, chemical fixation, and also because you cannot repeat it, you cannot measure the same leaf, and then biological variability can be a problem. So what we have been doing and working with researchers, physicists, and neutron physicists since a long time is that we were using neutrons and neutron scattering signals to study the structure of grana. So in this case, you need to go to a synchrotron or an area where you have particles, neutrons, a neutron beam, and these neutrons, and you can put your sample in the neutron beam, and if the sample has some structures which are grid-like, regular, like a granum, for example, which scatters the neutrons, then based on the pattern of the neutron scattering profile, you can calculate, physicists can help you to calculate the repeat distance values in a living plant. So the big advantage of this method, especially for research in these dehydrated or dry plants, is that you can put a living plant in the neutron beam, and we also put a desiccated plant. You measure the same grana, a larger area, millions of grana, get an average data, statistically and spatially averaged information on the granum structure. And if you have a good instrument, like in collaboration with the Oak Ridge National Laboratory in Tennessee, we had really nice time resolution of the data. So among the different plants, we also observed a little bit of changes between the control values. So we could measure several control leaves. And as you see, the values are a little bit higher than in case of the chemically fixed samples. That's due to the during the chemical fixation and then the embedding process, during dehydration of your electron microscopic sample, probably there is some shrinkage. So this is why neutron scattering data are higher. The repeat distance values of grana are higher than what you can observe in a resin-embedded chemically fixed sample. And although there is a biological variability also among control leaves and dry leaves, but basically with statistical comparison, again, we have clearly seen that the values obtained for dry leaves are smaller. So there is a shrinkage induced by desiccation in the grana, in the granum lumen, very probably. And what is the best, possibility to measure how these membranes are recovered and what happens during recovery is when we were putting dehydrated plants in the neutron beam, and then we were rehydrating the soil while measuring. We recorded the neutron scattering profile, then we watered the plant, and we have observed very nicely the shift of the scattering curve with time. And this shift is clearly indicating the dilatation, so that the shrinked membranes, which were the shrinkage was due to dehydration, but this was reversed after rewatering, and within 15 hours or within a day from lower repeat distance values, we got back to higher ones. So I don't think I will go into conclusions of the biological part. I just wanted to outline small angle neutron scattering as a method that enables you to study regular structures like grana. So we did not get any other structural information. So I think it's a nice way to compare in vivo, in fully in vitro conditions without any fixation, living plant material with your other data, for example, other structural data like electron microscopy. So in this plant, you can meet in hotel lobbies or in ornamental plant in green areas. I would like to thank my colleagues, especially Richard, who did most of the work, and the neutron physicists who were doing the physical work. And I'm glad for the organization and for being here. And I hope that next time maybe, or on another meeting, I will be able to talk to you about some of our works which were done on vegetative desiccation tolerant plants. Thank you.
Thank you so much. I do just want to make a real quick announcement for everyone. If we do happen to go over time, we will give each presenter their full allotted amount of time and just go over into the break a little bit. So don't worry about that. We'll try to get some questions asked for everybody. I did just see one question come in. It's from Olivia, and she said, "Beautiful talk. It was great to learn about your model. What is the water content of the leaves after 45 to 49 days of water deficit? Also, were samples fixed aqueously? And if so, is it possible that leaf segments rehydrated during sample preparation for EM?"
Okay, so the water content was 60% or around 60%, and it was 95 without the hydration. So it only went down to 60%. So only, I don't know what, when compared to these other plants or pollen grains or the desiccation, vegetative desiccation tolerant plants, which can go down up to 10%, it's relatively high. And then, the chemical fixation, and this is the biggest problem, I think, for electron microscopy on dry plants, is that, of course, you have a water, it was an aqueous solution, a buffer, phosphate buffer, and then glutaraldehyde. So this is why I think studying this fully in vivo is positive. And might provide other insights. Of course, we had similar data finally, but indeed, you cannot be sure what happens when you are fixing your sample in an aqueous solution.
All right, thank you. We have another question asking if you have had any research regarding identifying differentially expressed genes during this research.
Yes, on one of the slides we have transcriptomic data on the control and the desiccated plants, but the analyses are still ongoing, so I cannot share too much on that, but we were studying it because it could be really interesting. Thanks for the question.
Okay, thank you. It looks like we have no other questions, but if anyone still has questions, feel free to send them, and we'll get them answered. But we are going to move on to our next speaker. So thank you so much.